I'm Gilad from Yahoo Research here, and I'll be presenting a work on EvenDB, the key-value store optimized for spatial locality. So key-value stores provide a simple abstraction mapping keys to values. They provide single key operations such as put, get, and delete, as well as occasionally range query operations, also known as scan, that return keys and values within a given range of keys. Key-value stores need to deal with different workloads. Occasionally, those workloads are skewed. Namely, some keys are hotter or more popular in terms of reads, writes, scan, or all of the above. And for example, in this case, K6 is going to be more popular than K7. Now, in some cases, locality is exhibited not at the granularity of a single key, but rather at a complete range of keys. And this is what we call spatial locality. And this is common when keys are not just, do not contain just a single value or property, rather are composed of multiple properties. For example, this is what you get when you combine different fields or concatenate them and create a single key from them. And the benefit of using composite keys is that it allows the user to get a value based on multiple properties, which bypasses the limitation of a single index that's built in key-value store. So let's look at a specific example. One of our internal production systems stores mobile application events, which include the application name, timestamp, and other kinds of data. 1% of those applications, namely the most popular ones, contribute 94% of the events. Now, if we wanted to be able to analyze the events such that we can get the events that happened in a certain application over the last, say, minute, then we can store the data using composite keys such that the prefix is the application name and the suffix is the timestamp. And in this case, what we'll get is that 1% of the ranges is going to contribute 94% of the events. The most popular design of key-value stores is called LSM trees. In LSM trees, the most recent updates are stored in memory in a data structure called a memtable. And the rest of the keys and values are stored in several levels of files on disk. Now, those levels are in increasing size, in a factor of about 10 times larger, and their ranges overlap. From time to time, when a level gets full or passes a certain threshold, a compaction procedure kicks in, and the content of that level is merged into the level below it. So LSM trees storage is driven by writes. Namely, the most up-to-date writes are stored at the top in memory or at the top levels. And over time, writes propagate to the lower levels. So compactions merge potentially hot and cold ranges if we look at the read side. Namely, reads does not affect the location of the data, and hot keys might reach the lower levels. Further, since all levels cover the complete key range, namely overlap, when searching for a certain range of keys from a scan, we have to traverse all the levels in multiple files, since the keys included in that range might be spread across all those files and levels. EvenDB is an ordered key-value store that is persistent and offers fast recovery. It provides atomic operations, including scans, and it's optimized for spatial locality. It also offers low-write amplification. EvenDB relies on chunk-based organization, where chunks are much bigger than blocks, which are typically operating system pages, and also much smaller than common database shards, which are really large. So chunks are the basic unit for disk operation, including compactions, as well as memory caching and concurrency control. Chunk metadata is stored in memory as a linked list of chunk objects. Each chunk object holds metadata such as versions, synchronization mechanism, file handlers, and so on. And once a chunk passes the size limitation, it is just split. Now, in order to be able to reach the chunk that potentially contains the key we're interested in, we hold an index over all those chunks. Now, each chunk has its own storage we call func. That storage includes a log or a WAL, as well as an SS table, which is a sorted file that allows quick search. When we store a key in a certain chunk, that key is immediately stored within the log for persistent, and that log is occasionally merged into the SST in a procedure we call rebalance. Now, when we search a key that exists in a certain func, then we first search a row cache, which is a cache that stores particular hot keys. And then we search the log after going through the Bloom filters that are stored in memory. And lastly, we search the SST. And scans always search both the SST and the log because the keys might exist in both. Now, certain chunks might be very popular or very hot, in which case we'll create a memory caching we call a monk. A monk stores the complete key range within that's also stored in the SS table and the log, namely all the keys and values that are stored within that chunk. So when we store a key or update a key in a certain chunk, then that key is first stored in the log with its value, again, for persistence. And then it is stored in the monk. Occasionally, we rebalance the monk, which means we get rid of obsolete data and better arrange it for fast lookup. And rarely, we flush the monk to disk and create a new SS table. And this is just required in order to be able to flush the log and clear the log. Since this table is on disk, once we persist the data in the SS table, we can get rid of the log. Other than that, once we have a monk for a certain chunk, we never search the log, so we don't care if it grows infinitely, but that log occupies disk space, so we want to down the amount of space that it occupies. So when we search chunks that have a monk, we simply search the monk itself. It's a memory component, and we don't need to do anything else. And just to make something clear, monks are better suited for storing chunks which have many keys that are hot, which is typical to hot ranges. And this is as opposed to chunks that have single keys that are hot, in which case we better reserve the memory space and store that key in the row cache. So our evaluation of EvenDB included 3 benchmark suites. First, we used the traces from an internal production system, storing 1/4 of a terabyte. Next, we used standard YCSB benchmarks, which includes simple keys. And lastly, we used an extended YCSB benchmark, which included composite keys, which we synthetically create using YCSB. And our state-of-the-art LSM is RocksDB. So the first benchmark is ingestion, namely storing the complete data set of a quarter of a terabyte. And the graph shown here is a throughput timeline. Namely, it demonstrates the throughput of each database over time. And here, EvenDB is the blue line, and RocksDB is the dotted red line. What we can see here is that EvenDB maintains a much higher ingestion throughput, and therefore completes the workload 4 times faster, and also has a 4 times lower write amplification. One of the reasons EvenDB outperforms RocksDB can be seen when looking at the space amplification during the ingestion benchmark. The space amplification is basically the ratio between the amount of input generated by the application and the size of the database on disk. And in this case, we can see that RocksDB size grows significantly and then shrinks in a chainsaw pattern. And when that chainsaw drops, this means that compaction kicks in, and RocksDB uses a lot of resources to perform this compaction. And during that time, we can see on the throughput timeline on the right that the throughput indeed drops. EvenDB, on the other hand, it runs much more smoother, and compactions are done much more locally in the background without having a significant effect on throughput. And what we can also see is that most of the write amplification in EvenDB comes from the log space, which is the dotted line below. And this is mostly because we just don't care that the chunks that have monks, their logs grow because that does not affect us, the search performance. So EvenDB's advantages are first in-memory compactions, namely once a chunk gets hot, then it will have a monk, and that monk will observe most of the writes, and occasionally just write them back to disk to the SSD. And we also have localized compactions, namely when a chunk does not have a monk, then the compactions in which the log is merged into the SSD are local, namely they cover a relatively small range of keys. Another aspect that we looked into is scan throughput. Now here, this scan benchmark, again, a timeline throughput over time benchmark. This benchmark started immediately after the ingestion benchmark. And what we can see is that it took RocksDB almost 40 minutes to recover and optimize its data stores and reach a higher scan throughput, while EvenDB almost immediately reached a high scan throughput. So within this benchmark, EvenDB still wins. Now, RocksDB does run faster after it completes its storage optimization, but EvenDB does not try to optimize its storage in the background, and the scan through benchmark does not include many writes. So RocksDB has a lot of has the resources to optimize the storage without being affected by background updates. So in summary, EvenDB introduced a novel key-value storage architecture that's optimized for spatially local workloads. It offers slow write amplification, a single level of storage without overlapping, and the memory serves both reads and writes. EvenDB outperforms RocksDB when the workload is spatially local, or most of the working set fits in RAM, namely in the months. And otherwise, both databases are in par. And we've demonstrated EvenDB's benefits on real both workloads and synthetic YCSB benchmarks. And for that, I'd be happy to answer any questions.
Thank you very much for the great talk, Eran. Let's see if we have some questions on the Slack channel. I don't think we have questions there. So while we're still waiting for questions there, I have a couple of questions that I can ask. So I think in one of the slides you mentioned that RocksDB had like 4x slower ingestion rate compared to EvenDB. I was wondering like why that is the case and what is the exact workload that you ran? Is it like a sequential insertion of keys? Is it random insertion of keys? Can you provide more details of why RocksDB is so slow?
So the workload that we ran was the ingestion workload that reproduces the arrival of events from our production system. So those events are ordered by timeline, namely the actual order in which they arrived into the system, but they are indexed by the application name. So they have composite keys that are built by the application name and the timestamp. So what happens is that the insertion is distributed over the key range with hot areas because some keys are hotter, but it's not like tight sequential insertions like serial insertion where all the keys are adjacent. So I think what happened there is that we basically covered a fairly wide range of keys in RocksDB. When it had to do the compactions, then it had to merge files that covered a wide range of keys. And so compactions basically affected most or a significant portion of each level. And this caused RocksDB to do a lot of heavy compactions. Even though the amount of data wasn't huge, it affected a large range, and so the write amplification was significant. And in our case, EvenDB isn't really bothered by that because most of those local insertions take place in chunks that have months. So the compaction basically takes place in memory for the most part.
I see. So I think I have probably one other question that I can ask. This is probably a slightly high-level question, I think. So B plus trees already give you the spatial locality in that they don't do out-of-place updates. So like keys that are adjacent in the key space are going to be located sequentially on disk or whatever storage. So I was wondering, so is your requirement that you also need the high ingestion rates provided by LSMs while having the spatial locality? Is that why you want to optimize LSMs, not go with B trees or B plus trees?
So B trees in general, I think the main issue there is that insertions require, when you insert a single key, then you have to basically update a complete B tree node. And that's basically a random IO. So it might have worked better if insertions were spatially local. We didn't really try, a B tree baseline. So I'm not sure how that would affect, how this kind of workload would have affected an actual B tree implementation. But in general, we saw that B trees, that the insertions are, they generate more write amplification than LSMs that buffer inserts and do batch compactions, so are more efficient in writes.
Yeah, and I also see good reasons of why to optimize LSMs, which are already commonly used at many places to have this new property of supporting spatial locality lookups. Yeah, thank you for the great talk. I think let me see one last time if I have any questions. Yeah, so feel free to ask any questions that you have on the Slack channel for Eran. He'll be happy to answer there.